Hi, my name is Josh Joseph, and this is Lab 1 for Physics 2211. In this lab, we're using Newton's law of physics to analyze its effects on the real world. We're looking at Newton's first law that states that an object will not change its motion unless a force acts on it, and Newton's second law, which states that the force of an object is equal to its mass times acceleration. Ideal situation in this lab would be that no friction is acting on the moving ball. In this lab, we compare the computer model with the real world model. And the summary results is when comparing the slopes to the experimental and computational model, they're fairly similar, but near the end of the motion, the experimental model starts to veer away from the computational model. We'll look into this later on. Formulas and calculations used is that force equals mass times acceleration, velocity final equals velocity initial plus F net over mass times delta t. That's the code form of it. Position final equals position initial plus velocity average times delta t. That's the code form. And here are my calculations for the velocity, which came out to be 0.76 in the positive direction, only in the x direction, meters over second squared. Here are the free body diagrams of the ball. As we could see, initially when I pushed the ball, there were three forces applied: normal force, gravitational force, and applied force. Normal force and gravitational force are equal and opposite, so they cancel out. And applied force is me pushing against the ball. But after I push the ball, I no longer apply force on the ball. So there's only two forces applicable on the ball, and we're leading to the constant velocity. And the system and surrounding of this ball, lab would be the system being the tennis ball, while the surrounding would be the earth, ground, and the surrounding air, and other objects that the tennis ball interacts with. Now let's quickly look at the tracker and see how this looks. As we can see, I start around frame 35 because the before the ball was still accelerating, but around this time frame, we can see that there's a relatively constant velocity with the tennis ball, and on the right we can see the time frame as well as the associated exposition. Now let's look at the computational model. As we can see here, I adjusted the radius of the object to be the average radius of a tennis ball, as well as the mass to be the average mass of the tennis balls. The initial conditions of this lab would be that the ball started at the origin 0, 0, 0, and the initial velocity of the ball was 0.76 meters over second squared. Another thing I adjusted was the time to meet the time frame of the video. And when looking at the net force vector, since we said that the F net would be 0, I changed the vector from 1, 1, 1 to 0, 0, 0. We also applied the momentum principle in this code, as well as updating the ball's position based off velocity in this code. At the very end, it will print out the time as well as the ball position. When we run this code, we can see that it simulates a very similar reaction with our ball moving away from the origin. As you can see here, we got the time as well as the x position associated. Now let's look at the Excel sheet and compare the two different data points. As you can see, we have the data points for the computational and the experimental model. When we compare the two, we can see the linear regression lines for both the computational and experimental. And we can note that the slopes are fairly similar with R squared values that correspond with each one. But the key thing we should note is that in the beginning, the two slopes were very, very similar and even overlapping in the beginning. But over time, the experimental slope starts to veer away from the computational slope. So, what are some explanations for this? Well, the possible error could be that the tracking of the center of mass was due to human error because I was the one tracking every frame. And so not be accurate. It might not be totally accurate, leading to this difference in slopes. Another possible error is that the computational model does not account for friction and other outside forces acting on the tennis ball because we assume that F net is 0, and this is not applicable to experimental data, which experiences all these forces acting on the ball. So in the what if scenario, if the axes were switched, the speed will remain the same because it's a magnitude, but the velocity would change because of the vector and it deals with magnitude and direction. So if the ball was moving the positive x direction, it would flip and go to the negative x direction instead, and then changing the positive slope to a negative slope. So what does this mean? What it was asking, can we determine all the forces acting on the ball? And even though the ball is moving the constant velocity with the net force of 0, we really can't observe and determine all the forces acting on the ball. But the few forces that we can determine is on the y-axis, we can determine the gravitational or normal force acting on it. On the x-axis, there was the initial positive x force I acted onto the ball, and the negative x friction force present throughout the movement on the ball. In conclusion, in this lab we analyzed the movement of the tennis ball using the tracker, and then simulated this movement through a glowing scope, assuming there was no the F net was equal to 0, and compared the two models. As we said before, initially the global script was relatively uh, representing the data from the real world, but later on it started to veer away because we're started to ignore these other forces that made a bigger difference as time continued. Thank you.